So here we go. Here's our situation. The kitchen sink slowly draining. My wife pulled the plug 2 minutes ago, and at that time the height was 7.6 centimeters. And then 3 minutes later, the height was 5.8 centimeters. Assume that the water height decreased at a constant rate. So we want to define these variables with phrases. We want to be really specific. One-word answers is not going to do it. So time is not going to do it. All right? So we want to define all these variables with their definition, their meaning, and then if we know the value or values of it, then let's report that as well. Okay? So take a couple minutes to do that. And so we're going to use the standard convention that m is dy divided by dx. So we're going to use the standard convention that m is dy over dx. And so our water height is decreasing at a constant rate with respect to time. That locks in what x and y and dx and dy have to be. Okay?
Oh, wait, Mark. Sorry, Mark.
Yeah.
Is this file available for us, or?
No. So I didn't make this file available. Okay? Don't try to type the whole thing. The key thing is that you've got the you're going to define the meaning of those variables. Okay. Take a minute. I am. Thanks. And when you're ready, compare with the person next to you when you're ready to do that.
Oh, sorry for asking the question. When it says 3 minutes later, it means 3 minutes after those 2 minutes.
3 minutes after the time that it was 7.6 centimeters. So it was 7.6 centimeters. 3 minutes after that, later than the time it was 7.6 centimeters,
Okay.
it's 5.8 centimeters.
So it means 5 minutes after it's formed. Okay.
Yeah, uh-huh. Okay, see if you agree with what I'm saying. Is that what you came up with for the variables? Okay, should have. Okay, Do we have any known values of time in minutes? Known values of time in minutes. Okay, 2 minutes and 3 minutes. Agree? 2 minutes was a time and 3 minutes is a time. Aiden?
The other one is 5 minutes. It's 2 minutes and 5 minutes.
So what's the 3 minutes, Aiden?
That's the difference between 5 minutes.
Okay. So they gave us the number 3 minutes. What variable is that a value of?
Yeah.
That's a dx. Do you see? It says 3 minutes later. That's a 3 minute interval of time starting at the 2 minute mark. So that 3 minutes was a dx. Everyone see that? It's important, okay? And so that would give us another x value of 5 minutes if we wanted. We did a little calculation there, so we know there's 2 minutes is kind of a known value here, 5 minutes. All right, water heights. Do we have any known values? What do we know? 7.6 centimeters, 5.8 centimeters. Okay, do we have any changes in water heights? Okay, so we could calculate one, right? So we're not given any, but we've got 2 water heights, so we could calculate a change. I'll just write. And so how would we get the change in water height? Yeah. Okay, notice it's not just the bigger one minus the smaller one, right? It's final minus initial, not just the bigger minus the smaller. So we get negative 1.6 centimeters. Negative 1.8 centimeters. I'm just listening to you guys. Okay? So, constant rate of change. So, it's not given in the problem, but we can calculate it, right? We can calculate it. And so here's the thing. To calculate that, we're going to do the change in y over the change in x. So what is our change in height that we know? And what's our change in time? All right, so most of you said 3, okay? And that's correct. If you don't go through this procedure and you just go right for the constant rate of change, there's a mistake that lots of students make that you avoid making by doing this. And that mistake is, what do? They do dy is 5.8 minus 7.6 over, what is it that you think students do if they're not on top of what the variables mean? 3 minus 2. They say, oh, 3 minutes is the final time, 2 minutes is the initial time, 3 minus 2. All right? But 3 is not a value of x, it was a value of dx. Okay? So I could either write 5 minus 2 here or just by 3. And so we get that negative 0.06, and that's centimeters per minute. The negative indicating that our y value is? The height's decreasing, right? Y is decreasing. Changes in y for positive changes in time will be negative, and so we get a negative rate of change. Okay, this is all review. So this is the way you want to get started on contextual problems this whole semester. Defining variables and parameters, okay? Which are what, by the way? Parameters and variables are? Letters. Get it right on the test, okay? Known values for those, okay? Questions so far? All right, so I have plotted the point, that initial point. I thought I did, yeah, I did. Where is it? I turned it off. So here's that initial point that we know. What? 2 comma 7.6. That is a correspondence point in this relationship, right? 2 comma 7.6. So I'm going to take you through a process. So I want to know what's the corresponding height for 9 minutes after pulling the... So what's the correspondence point for 9 minutes after pulling the plug? So 9 comma what? What's the height of the water at 9 minutes after pulling the plug? It's going to take you through a process here that's really important because it's going to apply all this stuff that we've been learning about constant rate of change. Okay? And so the first step in that process is find the change in x. So I'm going to use this reference point. At 2 minutes, the height was 7.6. I want to know what the height is at 9 minutes. What's dx? How do we calculate dx? Final minus initial equals the change in x. Okay, and that's a long way here. I'm gonna, so I can draw a better line. I'm gonna zoom in on the. Yeah, thanks. You're absolutely right. That is minutes, not centimeters. Thank you. You should have all been thinking that. Should have all been thinking that. That was definitely minutes. Okay, and so how can we represent that on the graph? So here is 9. So starting at 2. A change of time of 7 minutes up to a final time of 9 minutes. Something like that. And that's our dx equals 7 minutes. Okay, so now what do I want to do next? I want to find dy. But I can't do final minus initial because it's the final y that I'm trying to find. So I need another way to calculate dy. All right, so do we have constant rate of change? If we have constant rate of change, we have this powerful way of finding what dy is with constant rate of change, which is m dx. I just found dx. So what is my constant rate? Negative 0.6. And what does that constant rate mean? It means for any change in time, the change in height is negative 0.6 times the change in time. We worked hard on that, right? Given any change in time, dx, the change in height is negative 0.6 times that change in time. Is that negative 4.2? Units on that? That's centimeters. Okay, and now we're going to use another thing we learned. What do we want to do? Now we want to know what the final y is. We've got everything we need to calculate the final y. So y final. Y final is, yeah. Right, so remember, it should make sense. So we started at 7.6, that's y initial. How much did y change? Negative 4.2. It went down 4.2, so we're going to take 7.6, and we're going to add the change in y. And we're going to get negative 3.4. No, 3.4. And so, what happened? So for a change of x of 7, where's that going to be about there? Y went down. How much? So our dy was negative 4.2, and so we take the initial y, 7.6, plus the change in y gives us the final value of y. So now we have that correspondence point, which is 9, 3.4. So now we're putting to work. We're putting to work all this stuff we've done in the last week. dx is the change in x, final value of x minus initial value of x. That's our change in time. We've got constant rate of change, so we know, given a change in time, we know what the change in height is. We use our constant rate of change. And then we know that the final value of y will be its initial value, what we started at, 7.6, plus the change in y, negative 4.2. This is all the stuff we've been working on the last week, and now we can put it to work. And what did we do? We had one correspondence point of this relationship, and it allowed us to find another. It allows us to find another one. That at 9 minutes, the height is 3.4. So what we really want, though, is I want to represent every correspondence point. That would be the most powerful thing we could do, or the most significant thing that we could do would be to represent every single correspondence point of time and height. So the way we do that, we're going to use the same process, but instead of picking an actual final time, we're just going to call it arbitrary. So we're just going to say, let's graph the other point so I can. What was the other correspondence point that we have? 5, comma 5.8. All right, so I can get some more accurate. So what I'm going to do now is I'm just going to just pick a point here and don't look at what the value, don't look at the axes, but it's just going to represent any correspondence point of time and height. So how can I represent that? If that represents any and every correspondence point of time and height, what can I call it? Yeah. What do we call it? X and? No, y, right? Yeah, we can make a function. Yes, we can make a function, but we'll just stick with x and y for now. But absolutely, we could define a function of height as a function of time. We'll just use our x and y that we've already defined so far. Okay, so we did that up here. So x is our time, y is our water height. So by calling a point x comma y, it could be this point, it could be this point, it could be this point, it could be this one. I could have drawn it anywhere. So I'm not trying to draw it at 7 or 6.9 or anything like that. It's just I could have put it here, I could have put it here, here, here. It represents every single correspondence point. Now we're going to do the same process again. Let's go back to our original point here, which was what? 2, comma 7.6. And now with this final point just being this arbitrary point x and y, we're going to go through that same process. We're going to first find what? Find the change in x first. Okay? But now it's going to have a variable in it. It's not going to be a number. It's going to be an expression that can change based on what x is, right? And then, based on that, we're going to find dy. Again, this will be an expression. It won't be a value like we had before, because it's going to be based on whatever x is. So this is going to be an expression of x, and then we're going to represent y final. By y final, I'm talking about this right here. This is y final. And that y final is any y final, right? Because the x could be any x amount of time, and then we want the corresponding y, which is y final. All right, see if you can do it. So we did it with a number, so now let's just do it with this arbitrary time value x. Work through the same process. And what we're going to have when we finish is we're going to have an expression that represents every correspondence point of time and height. Not just one like we did before. See if you can do it. I should have put represent for all of these, because we're not really finding a value, we're representing each of those. Okay. Headphones. You guys should be wearing no headphones in lecture, please. Can't possibly be concentrating with headphones on. All right. Somebody new. Were you able to represent or express dx? Express dx. Yes, ma'am. What was it? She wants x minus 2. Everyone agree with that? Yeah. X minus 2. Still final minus initial, it's just that it could be any x minus our initial 2. Okay, somebody new. Represent or express dy. Yes, in the back. M times the change in x, which we just found. Right? If we have constant rate of change, changes in y are m times changes in x. We worked hard on that. And we're going to use it all semester, okay? Finally, representing y final. Jacob.
Well, for number 2,
Yeah.
you distribute the negative 0.6 to the x negative?
Yeah, but we don't want to because this really preserves that meaning of m dx. When you do that, now you're looking at it, you don't know what you're looking at, really. But yes, it's okay. It has the same value. It's the same expression. Okay. Yeah?
Could you also just put y minus 7.6? Or do you want us to
No, because in the end we're trying to find what that is. So we don't want to put y final minus 7.6 here because in the end we're trying to express y final. So we don't want to use that along the way. We want to use our constant rate of change, m dx. Okay, yeah.
Let's see. For the 7.6 minus y.
7.6. Nope. So y final is the same one that you were asking about in the quiz too. To get a final value of a quantity, it's the initial,
Is it plus y?
not plus y. Yeah. Yeah, I'm sorry. Go ahead.
Sorry, it's going to be plus the change in y,
Plus the-
which is the negative 0.6 times.
Plus the change in y. And it should make sense. Initial value of a quantity plus its change gives you the final value. That should make sense. Initial value of the quantity plus the change in the quantity. All right, so what do we just come up with? So what is this? This is a equation or a relationship of x and y that gives us every single point, every single correspondence point of x and y. So rather than doing them all one at a time, right, and there's an infinite number of them, in the previous example, we just did one particular correspondence point. We can just do this, and we get them all. We get them all. So if at 8 minutes, right, if x is 8 minutes since the plug was pulled, we can replace x with 8, and it tells us what the corresponding height is. Okay? So this expresses all correspondence points. Okay, and so in it's also the equation of the line or curve or whatever we're going to get. So let's and so we want to make it into a function. Sure, we can make it into a function. So we can define let's define a function. What do we want? What name of the function do we want to use? F. Okay, we can use any letter to be the name. F is what we're most common. F is fine. All right, and that is, the rule is 7.6. I'll just go right to minus. It'll change it anyway. If I do plus 9 minus, x minus 2. All right, so now, will that graph it? Is that going to graph it? Is it going to show me all the correspondence points? No, that just defined the function, that's all. So what do we need to do to graph it? Y equals f of x. And let's show it from, say, x to, let's just do 15 to make sure that we got all the possible time. But that That may be after it's finished draining. Hopefully it is, so we'll see it all. So now when I graph this, what is it going to show? It's going to show all correspondence points of, oh, hey, pretty good guess, 15. A little bit less than 15 minutes to drain. So this is now, what you're looking at is all correspondence points of time and height. It just takes too long to draw it that way, right? It takes too long to show it, to show what it actually is. Like, you know, get your pillow, right? Okay, so it's a lot easier just to go like that and just know what you're looking at when you're looking at it, which is an infinite number of points, okay? Okay, any questions on this very important process of, so what is kind of, this is also the equation of the line, okay? But now we're focusing on what the meaning of that is. So the days of y equals mx plus b are over, okay? We're building this other form that's based on everything we've done so far. It uses basically on change of x, change of y final equals initial plus change. But what we get is the equation of the line, which expresses all the correspondence points. Now, if we multiplied this out and rearranged it, yes, we could get it in the form mx plus b. Okay? But this, in terms of creating models for constant rate of change, this is going to be a lot more useful to us than this. All right? And it's a lot more meaningful, right? Everything we're looking at there has meaning, right? Constant rate of change, a particular correspondence point. This over here is the change in y. So there's so much going on here that you can just see in that form. Okay, any questions on that? Super important process for finding equation of the line. So we need a different one. Let's find our crickets problem. That's a bucket. Here we go. Here we go. So can we do this? So the temperature percent. So you got a problem on this earlier. Okay, temperature in percent Fahrenheit changes at a constant rate with respect to the number of times cricket chirps in a minute. You count 100 chirps when the temperature is 98, 96 chirps when the temperature is 81. Okay, so what we want is, for time's sake, we'll just kind of go through this fast because we really want to practice this, building that relationship of all correspondence points. So given our goal is a relationship that gives temperature as a function of number of chirps. We want to represent all correspondence points of temperature as a function of number of chirps. We're going to start with what is x, y, dx, dy, and m. So can we go fast? What would x be? Number of chirps. What's y? Temperature. Dx. Change in number of chirps. Dy. Change in temperature. How do we find the constant rate of change then? It's going to be dy divided by dx. Do it. Do it. Find the value of the constant rate. Change in temperature. over change in number of chirps. I got 4.25. Did you get that too? No. Did I make a mistake? They're backwards. 100 chirps when the temperature 96. I think it's right. Is it right? I started that way. So what is dy? dy is temperature. Number of chirps. This is right. Right? I just picked the first point to be the final, and it doesn't. So okay, sorry. So you want 81 minus 98, and 96 minus 100. I know it's the same, but that will make people happy. Okay. Now is it right? Okay, cool. So we have a correspondence point. What is our correspondence point? We'll do 100 and 98. And let's graph that point. And so what is our goal? Our goal is to represent all possible correspondence points. So we pick a point out here. Let's use the other. What was the other correspondence point? Let's use the other one. Why doesn't it go there? There we go. Okay, so then we can look. We're going to say we want every correspondence point, and I don't know where those are, but I'm just going to draw one. Oh, right. My pen switched. Oops. Okay, I found it. All right, here we go. So I got some other correspondence point here, and that's going to be X and Y. This was our point, what, 96, 81? 96 chirps, 81 degrees. Is that right? And then X and Y. Okay, so I want you to find the relationship of all correspondence points of chirps and temperature. Build that relationship from scratch, the way we practiced it before. So another chance to do that. Go. Got it. Okay, somebody, all right, so don't pack up and tune out, okay? I know we just only have a minute left, but it's super important. You need practice at this. Somebody new, express dx. Yes, sir. Yeah. No. So take me through it. So I never want just answers. I always want process. So take me. Okay, so I'm asking, how do we express dx? dx. What is it? X minus 96. And then behind him, you had your hand up. How did we get dy? Yeah, you had your hand up. Yep, it's going to be the constant rate times the change in X. Then final, somebody new, yes?
It's the initial value of y1 plus the change in x.
So this process does so much work for us because it gives us a representation of every single correspondence point of number of chirps and temperature. Given any number of chirps, it tells us what the corresponding temperature is.